So today I want to talk about limits. And limits is a topic that we've already seen. We saw it in a previous video where we talked about how limits are ways in mathematics that you can broach the concept of infinity. And for example, we had this function f of x equals 1 over x, and we observed that the limit as x goes to infinity of f of x equals 0. So what we're saying here is that as x gets closer and closer to infinity, as you put higher and higher numbers into this function, the output of the function gets closer and closer to 0. As x approaches infinity, f of x approaches 0. That's how to read something like this. And that sort of makes intuitive sense for this case, because as you put higher and higher numbers into the denominator, the overall fraction gets lower and lower, gets closer and closer to 0. Okay, so let's think about in general now, what does it mean to say the limit as x approaches infinity of f of x, where now this is just some random function, equals a, where a is some value. It doesn't need to be 0, it could be any value. What does this mean? And the answer is what it means can be cashed out using quantifiers in a clever enough way. And if you want to remind yourself about quantifiers, I have another video on quantifiers that you can take a look at. So what does it mean? Like we said before, it means that as I put higher and higher values of x in, f of x gets as close to a as I want it to get. And that's what we need to start with to express this using quantifiers. We need to say, no matter how close I want f of x to get to a, I can make it that close by just putting x to be a high enough number. So the way to say no matter how close I want f of x to get to a is with a universal quantifier. So we say for every epsilon greater than 0. And you should think of epsilon here as kind of like a measure of closeness. Right? Epsilon is some number, some very small positive number that tells you how close do you really want f of x to be to a. And I'm saying no matter how close you want it to be, that's the universal quantifier, no matter how close I want f of x to be to a. Now the f of x and a part are going to come later. But this is like saying no matter how close I want to get, now I need to say I can do it. And saying I can do it is to say there exists an n, and think of this as like a threshold for the input. We want to say there exists a level above which, as long as x is above that level, then f of x is going to be this close to a. So the way that we say that is, if x is bigger than n, as long as I choose a number x which is bigger than this threshold level, then that works to guarantee that my output of the function, f of x, that its distance from a is less than epsilon. And here I'm using the difference between f of x and a in absolute values to express the distance between the output of the function and this value a, which is supposedly the limit. So I also have a video on using absolute value to talk about distance in that way. So once again, the definition of a limit, at least this type of limit, and the limit as x goes to infinity of f of x equals a, is cashed out by saying, look, no matter how close I want f of x to get to a, no matter how close, the for all is it's like saying no matter how close, no matter what degree of precision I desire, there exists a number n big enough so that as long as my input x is bigger than n, right, which is x is approaching infinity, so I'm saying as long as x is big enough, sort of like close enough to infinity in a sense, then the difference, the distance between f of x and a is as small as desired. So this is how you use quantifiers, or universal and existential quantifiers, to express the concept of a limit that involves infinity. And indeed, all limits are expressed using quantifiers in this way.